Okay, so we're going to get into start talking about the functions of the different parts of the nephron and the mechanisms that control each of these, right? So if you remember, kind of the major functions that we have in the kidney are filtration, reabsorption, and secretion, right? And so the first part of the nephron is responsible for that first function, which is filtration. Okay, so this is kind of where we started, and we talked a little bit about the blood flow to each nephron comes through a arterial, right, the smallest arteries, which is called the afferent arterial, which is going to deliver blood to a capillary bed. That capillary bed is basically scrunched into a ball of capillaries that fits inside of a balloon-shaped sac called the Bowman's capsule, right? And will then exit, the blood flow will then exit through the efferent arterial and become another capillary bed that is going to kind of drape over the rest of the nephron. And it's called the vasorectum mostly. And peritubular capillaries. We're going to talk about this structure here. Let's talk about the renal corpuscle here, and its structure is a really nice example of form equals function. So we have two layers to our renal corpuscle. It's a double layered sac, if you will. The outer layer is a simple squamous epithelium that is called Bowman's capsule. Or sometimes it's simply just called the parietal layer of the renal corpuscle. So parietal meaning the outer layer. There's also an inner layer that's adhered to the surface of the capillaries, and you can see it there in purple. And these are some of the more specialized cells. And they're often called the visceral layer. The visceral layer of the renal corpuscle. Visceral meaning they're associated directly on the surface or the capillaries here, or the inner layer of the sac. So whenever you see a membrane, often they call them serosal membranes. They'll often have a parietal and a visceral layer. Now the visceral layer in purple here is made up of specialized cells called podocytes. And we're going to talk about those podocytes, but what they do is they wrap around the capillaries and form the sieve, or the screen of the filter, and help control what size you have to be to leave the blood and enter the Bowman's space. Bowman's space is the space between the visceral and parietal layer. So basically, if I'm a solute in the blood and I travel into the glomerulus and I'm small enough, I'll leave the capillary between the podocyte pedicels, which are the small feet-like projections we'll talk about in a second, and enter Bowman's space. And once I'm in Bowman's space with the water of the plasma that is leaked, I'm now part of the filtrate, right? Or what we call primary urine, and that will enter the rest of the nephron, right? The tubular part of the nephron we call the renal tubule. And then it will be modified, right, as it goes through the renal tubule. And what we end up with is the definitive urine that ends up in the calyces, the renal pelvis, and then out to the bladder. Now, what this picture here shows you is a blow-up kind of the wall of the capillary, and then the organization of these podocytes, all right, these specialized cells. And so you can see on this side here, which is our right side, right? This is the capillary lumen. These are the blood cells. Here is the endothelium. Okay, endothelium is the simple squamous epithelium that lines the whole cardiovascular system. Okay, and in this instance, the endothelium is very leaky. It is very fenestrated. All right, so remember, fenestrations are holes. And so these holes are of a certain size. They're really small, obviously too small for blood cells. And plasma can leak and also maybe some larger proteins can leak through those holes and work their way through the basement membranes, and then maybe squeeze between these foot-like projections that are in purple, which are the pedicels, or the cellular processes of the podocyte. And if I can squeeze between those, then I will enter Bowman's space. Now, the one thing you'll see here is there's a little line that crosses between the feet, kind of stitching them together, and this is called the slit membrane. And it is a glycoproteaceous secretion, so it's made up of glycoproteins, that is a screen. And if I'm a really big protein that can fit through these holes, I'm going to bounce off that screen and stay in the blood. And so it's basically a screen of certain size. You have to be smaller. Have you ever heard of proteins that are like in Daltons, is the size that they call them? You have to be of a certain Dalton size to actually fit through those holes. And so really large proteins also will not enter the filtrate because they can't fit through the slit membrane. A wonderful example of that is a protein called albumin. So albumin is a really large protein. You probably heard of albumin before. It's found in eggs, right? It's what you eat. It's the white of the egg. It's what you eat. Well, you produce albumin too, and it's a liver protein. So the liver produces it in all vertebrates. We produce it as an osmotic sponge, all right? And I'm going to explain what that is in a little while. But albumin's too big to fit through the slit membrane. It fits through the fenestration easily, but bounces off the slit membrane and enters back into the blood. It can't enter the filtrate. So it's too big. And many of the big proteins are. So I'm going to explain how these feet-like processes are organized as we move into the next slide. So this is a picture of the cortex right here. And then if I could draw, you see this line, this black line I've given you right here? So above the black line is the cortex. Below the black line is the medulla. And notice that it's only above the line that you see all those little circles, right? All these little circles here are renal corpuscles. And here's one renal corpuscle blown up, right down here. And you can see there's a simple squamous epithelium on the outside. That is called the parietal layer or Bowman's capsule, right? This is the afferent arteriole coming in, right here. It's wide. These are the capillaries. And then the podocytes are hard to see there because it's not stained very well, but the podocytes are also sitting on top of this large glomerular capillary that fits within the renal corpuscle. And this white space between the blood vessels and Bowman's capsule is Bowman's space, or the renal space, where the urine is collected, the filtrate is collected from the glomeruli. Now, anything that ends up in the Bowman space is going to end up in the first part of the renal tubule, which we're going to call the proximal convoluted tubule, all right, or PCT. Now, obviously, not all the plasma leaks into this space. It's about 25%, if you really wanted to know. Now, where do the numbers come from? Mostly I give you mammal numbers, right? So 25% of the plasma actually enters Bowman space, and that's a lot. It's a lot. It's a very good filter. It's a very effective filter. So here's a couple pictures of the podocytes, and these are fantastic images here. These are SEM images that show the inside of a renal corpuscle. And so this is the ball of glomeruli. And the thing is, when you're looking at this picture, you can't see the capillaries. They're completely covered or surrounded by the podocytes. So the only thing that you can really see are these little bumps, right? These that are everywhere, that are the cell bodies of these cells. So like a neuron, they have a big cell body and then one long process. You know how neurons have an axon, right? One long process. Here we don't have any dendrites. We have a cell body and a really long process. And what we're going to take with this rope or long process is we're going to wrap it around the capillaries really tightly. And so when you look at this, you can see that there are little wraps, really large wraps, that have smaller processes that come off of them. And then the smaller processes wrap around each glomerular capillary. So here's a nice drawing. Here's a podocyte. And here are some of these major processes that come off. There's actually more than one. There can be several. But they come off, and then they send little wraps, and they wrap really tightly around the actual glomerular capillary. And you can see the arms between wraps are basically as close together as you can get. It's like wrapping yarn really tightly around a tube, right? So that there's very little space between the yarn wraps, if you will. And that's what you see here. And that is the sieve. And not only is it the space, but then these processes produce that glycoprotein slit membrane. That's a film that you have to pass through, like screen, in order to leave the blood and enter Bowman's space. So this is the other thing I love about this picture is it shows you the actual capillary here, right? So this is this yellow circle that has a bunch of holes in it. That's the endothelium. It looks like somebody took an Uzi or a machine gun and blew a bunch of holes in it, right? It's very porous. It's very leaky. So it will leak plasma. Now these are small holes, you know, they're like 0.01 microns or something. They're really small. So you can leak through them if you're dissolved or if you're a large protein. And then you're going to hit the basement membrane. And if you remember basement membranes, they have collagen. And collagen acts like kind of like a screen, right? Kind of limits how things can move. If you can't move through the collagen in the basement membrane, you're just going to bounce back into the blood, right? You're going to enter back in through those holes. If you can fit through the fenestrations, the holes, and the basement membrane, then you have to squeeze between the pedicels, right? The pedicels are these feet-like projections. That's what each of these little, wrappings are called pedicels. And there's a slit membrane between them or a screen. I got to squeeze through that too. If I'm small enough, I'll enter that, right? I'll enter into Bowman's space. So that's the sieve, is really the slit membrane and the very tightly wrapped pedicels. So again, this is a blow up of this area right here. Higher magnification, you can see the cell bodies here, and you can see the multiple wraps coming off. This is a capillary. You can't even see the surface of it, right? It's so tightly wrapped so that these can perform that really interesting function of filtration. It's a really good example of form and function, right? We all good with that? Okay, three main functions here of the nephron: filtration, reabsorption, and secretion. Notice this slide also has a fourth one, which is urine excretion. Well, of course, what's the nephron doing? It's producing a wastewater, isn't it? We call it urine. And that urine is going to leave the body. You're cleaning the blood, correct? Is what you're doing. And everybody always wants to know, well, what are you cleaning the blood of? Anything that you consider a waste, right? And what does your body consider a waste? Anything in excess. Anything that is in excess, your body really doesn't need, it's going to try to get rid of. So if you have too much water, you're going to get rid of it, right? If you have too much glucose in your blood, your kidneys are going to get rid of it. So if you have really high blood sugar, for example, that's not good. Normally you're going to find it in your urine. So anything that's in excess, you can dump into the urine. And so we're going to talk about now how we modify that filtrate that is entered into the renal tubule. And that's really the job, this reabsorption and secretion of the renal tubule, right? So the corpuscle does filtration and the renal tubule does reabsorption and secretion. So you notice we have afferent arteriole delivering blood to our glomerulus, which is sitting in my renal corpuscle. It is drained by the efferent arteriole that then gives rise to peritubular and vasorectal capillaries, which are surrounding the renal tubule. So they are participating, these other capillary beds, the peritubular capillary bed and the vasa recta, are participating in reabsorption and secretion, right? How? Well, they're the ones that are receiving the materials from the filtrate when you reabsorb things, and they're the ones adding stuff to the filtrate when you secrete it. Right? That's the movement. If I'm moving from the filtrate back into the peritubular capillary, it's reabsorption. If I'm moving from the capillary back into the filtrate, that's secretion. Okay? So let's talk about how you do that, because what's controlling these two processes, is the epithelial lining of the renal tubule. So before I jump into that, let's just talk about the filtration power. What's driving filtration of the renal corpuscle? It's blood pressure. All right, so blood pressure in vertebrates is driving filtration. All right, it is the actual mechanism or pressure that's needed to force fluid from the capillaries into Bowman's space. All right, and the problem here is we got a couple of different pressures, if you will. Right, we have blood pressure, and blood pressure often on these figures is called hydrostatic hydrostatic pressure, right? Which is water pressure, or we just call it water pressure, right? And there is another water pressure that's pushing against blood pressure, and it's the hydrostatic pressure of the capsular space. If you fill a balloon, it has its own pressure, doesn't it? Right? It pushes back a little bit. There is also a third pressure called osmotic colloid pressure, which is right here. Right, and I'm gonna explain to you what that is. So you got kind of three pressures you have to deal with here. And notice one is positive, which we call blood pressure, and the other two are negative. And in this instance, notice the numbers are small because this is kilopascals. It's a unit of pressure. If you've had physics, it's a big unit of pressure, right? You could also use millimeters of mercury, and the numbers would be much bigger. They're just two different ways to represent the same numbers, okay? So what you notice here is that there is a very small difference between blood pressure and the two negative pressures, right? But you do get a positive filtration pressure. And it's small, but it is positive, and it will force fluid through the slit membranes into Bowman's space, right? But notice, if blood pressure drops even a little bit, it's going to dramatically affect filtration power, right? So you don't have to drop blood pressure very much in order to change filtration rate, right? Which is going to be one of these controlled conditions that we've talked so much about. So homeostatically, you need to be filtering blood at a certain rate all of the time, and blood pressure is stringently controlled and monitored at the afferent arteriole. That is, the kidneys are self-monitor. They're monitoring blood pressure of the afferent arteriole 24 hours a day, 7 days a week. And if blood pressure increases in your body or decreases in your body, your your kidneys will respond and change blood flow in the afferent arteriole. And we'll talk about that towards the end because it's kind of a neat mechanism. So what are these other pressures? So as I mentioned, let's go to this slide here. So I just like the drawing a little better. This is for humans or of a mammal of similar size. All right, we have hydrostatic pressure here, right? HP of the glomerular capillary. So that says HP of GC. GC is the glomerular capillary. So that's the blood pressure, this first one. Notice now we're in millimeters of mercury. It's about 55 millimeters of mercury. And this is for humans because it's easy to find those numbers. There is a pressure pushing back because there's fluid in the glomerular capsule and it can only leave so quickly, right? And that's called the hydrostatic pressure of CS, which is capsular pressure, or the capsule pressure. So that's water pushing back. Notice it's about 15 millimeters of mercury. And then we have this other one called OP of the glomerular capillaries. And that's the colloid osmotic pressure. So what is that? That is what I like to call water sponges. So your liver produces these, and that's why I used albumin as my example. These huge proteins called albumins. Albumins have multiple functions, but one of the major functions of albumin is to act as a water attractant in the blood supply. All right, and you might wonder why, right? And here's the reason why. If you have a leaky capillary, and there are leaky capillaries everywhere, not just the kidneys, you don't want all the plasma leaving, right? You want some of the plasma to stay so that you can force it back into circulation. And so what the albumins do, and your liver produces these consistently all the time throughout your life so that you have a certain concentration of albumin flowing through your blood supply. What the albumin does is draw plasma back into the capillaries when it leaks. All right, so you have a flow rate here, and if you allow a certain amount of plasma to enter the interstitial space, it will be sucked back in like a sponge because it's attracted back to the albumins. Albumins are huge glycoproteins. The sugars attract water, so they help prevent too much plasma from leaving. Does that make sense? Have you ever seen they put those sad commercials on with the starving African babies, and they have those huge bellies, right? And they're starving, they look pathetic. They have huge stomachs. Or somebody who has severe liver disease will have a huge stomach. Why? Because those are leaky capillaries in the intestines. They're leaky on purpose so that you can take up nutrients easily. But if their livers aren't working, they're not producing these. And so instead of reabsorbing a lot of that plasma back into the blood, sucking it back in, you've lost that ability. So where does it sit? It sits in the interstitial fluid. It's going to sit where the capillaries are the most leaky, which is the intestines. And so that's why they get big bellies like that and they start having lots of interstitial fluid. Does that make sense? So that's kind of how this works. And so that osmotic pressure is pretty high, right? 30 millimeters of mercury. That's consistent across the whole cardiovascular system. Yep.
So, I was able to shadow a cardiometabolic doctor. He's seen a lot of people that had like heart problems, but they also had kidney issues. They always had a bunch of fluid built up in their legs. And like you could like press into it and hold it the shape.
Edema.
Yeah, edema. There's like the capillaries that are like in your leg. Are they leaking too? And that's why there's like a buildup of fluid in your legs too.
Exactly. Yeah. And the problem is when you get to the heart now, we not only have to worry about flow and pressure, but if one part of the heart is not functioning because it's two pumps, then blood backs up. And when blood backs up, it increases the hydrostatic pressure in the legs, particular because of gravity, right? So if you're not returning blood back to the heart fast enough because the heart's failing, then it's going to back up in your system because it's all closed, it's all connected.
Yep.
And so what happens now is your hydrostatic pressure gets so large in those capillaries that it overpowers this, and then you hold fluid, you retain fluid. Yeah. And so they got to give you a diuretic, right, to help the kidneys like move that water. It's incredible, man. They can bring somebody in with huge legs, and they'll move 30 liters of fluid out of their legs. It's crazy. Yeah. And that's when you have right side or left side heart failure. It's usually right side heart failure. Sorry, that's what happens. Now, if you get left, your left starts failing, and it starts backing up in your lungs. Yeah, which you drown.
Yeah.
I mean, you literally drown. Isn't that right? That's weird, right? But anyway, yeah. So that's what. So you got to add that kind of gravity pressure.
Yeah.
So it's all about and this is the same thing that happens when you cut your hand, and it gets red and swollen and really hot, right? If you've ever had an infection, like I bite my nails, and it happens sometimes, right? Because I'm terrible at biting my nails. Because I had bacteria from my mouth to my nails, and it was disgusting, and I get an infection. And it gets really hot and red. So what's happening there? You're using a new hormone called histamine, and it increases hydrostatic pressure to that area, which overpowers this, and now you have tons of plasma entering that area, and it gets but it's really local, right? Because that's the only place that histamine is being released, which delivers white blood cells to the infection. Again, once you understand the foundation, you can start understanding how all those little things work. And we'll talk about a little bit about edema when we get there.
It's really weird.
Okay, the cardiovascular system it's tough. It's tough to understand and keep all the little nuances together because there's a lot of stuff going on. I give you a little of it, but yeah, so we can talk about that. Now this again, if you subtract all of these, look, it's only a net positive of 10 millimeters of mercury. So it's really important that your blood pressure stays high. So if you have really low blood pressure, like my wife's mom, grandma, she doesn't drink. She has low blood pressure anyway, and her kidneys don't work, right? She feels terrible all the time because her blood volume is really low. Her blood pressure is already really low. And so what's happening? This number's dropping, right? Dropping. And her filtration power is negligible. So, she's just ruining her kidneys. Try to tell her this, but she won't drink because she doesn't like to pee. Which you should be going to the bathroom a lot, all of you, drinking lots of fluids, right? Particularly water. I know I'm just as bad. Anyway, so this is how this works. Remember, if your kidneys stop working, you die. Right? You don't want to ruin your kidneys. So, does this make sense? Now, this filter is really effective in mammals. Look at this, in humans. Or a mammal of a human size, or even bigger. Think of bigger mammals, even the filtration rate would be higher. 125 mils of plasma are entering Bowman's capsules in your kidneys every minute of every day. You only have 6 to 8 liters of blood in you, right? 125 mils. That's 180 liters a day. That is called glomerular filtration rate. So in a mammal, our kidneys are really effective because we have really high blood pressure. Now, obviously, if I have 8 liters of blood, I'm reabsorbing most of that, right? You can already see the nephron's main job is reabsorption, right? I'm going to reabsorb all that. And you might be like, this is really counterintuitive, but you have to get, if you want to clean a fluid, you have to pass it into the filter, right? And then you need to reabsorb it. So, and that's what you do here is you reabsorb the good stuff and leave the waste afterwards. Now, salamanders, my favorite animals, amphibians, they have much smaller filtration rates. So instead of 125 mils, it's about 0.1 mil per minute. It's much smaller because their blood pressure is much lower. Their hearts are not nearly as powerful of a pump. And they don't produce near the blood pressure that we do. Their flow rate's a lot slower. And that's because they're cold-blooded, right? And their oxygen demand is not as high as ours. All right, so far so good? So that's kind of how this works. Now we can start talking about, all right, we got this really effective filter. We have lots of filtrate. And obviously, we're going to reabsorb it. And really, the first job of the first part of the renal tubule is to do that. The first part of the renal tubule is called the PCT, or the proximal convoluted tubule. And it absorbs 70% of what entered from the renal corpuscle. So if you take 180 liters and multiply it by 0.7, it absorbs that much. Most of the filtrate goes right back in to the blood supply. Where is it going? Right back into those peritubular capillaries. This epithelium is really good at absorbing, anything that's really good for you. So, for example, glucose, amino acids, small proteins, other organic molecules are small enough to fit through the sieve. They enter the filtrate, right? They enter the filtrate. But the PCT will absorb 100% of those things. Glucose, 100% of it should be reabsorbed. Any amino acids or small proteins, 100% of those are reabsorbed immediately. And they are reabsorbed through what's called an organic symporter. all right? Organic compounds importer. So you could put amino acids here. You could put other sugars here. You could put small proteins here. You could put urea here. You could put any organic molecule will have a symporter that is a sodium symporter. See that? That is really effective at reabsorbing it from the tubular fluid here on the left, which is the filtrate, and the blood over here, which is the peritubular capillaries, right? So, unless your blood glucose is high, or you're dumping a lot of amino acids because of muscle breakdown or something, that stuff's not going to end up in your filtrate, right? Now, if you're pushing more protein into your filtrate than you should, and you might ask, well, when would you do that? You take a shot to the kidney and you damage the filtration sieve, or you have really high blood pressure, and you have too much blood pressure, and you're pushing too much protein in, then you might end up with protein in your urine, which isn't good. Or if you have glucose in your urine, it's probably because you have high blood glucose, uncontrolled diabetes, which is horrible on the kidneys and the circulatory system. So you absorb 70% of your filtrate in the PCT, and you remove anything, 100% of anything that's really organic, if you're pretty normal as far as your concentrations of glucose. Now you also got to control, notice here, how much sodium chloride actually enters your urine. Now, sodium chloride is the most common two ions in your interstitial fluid. They are also the basis of your electrochemical gradients and the function of nerves and muscles, right? So it's not surprising that sodium chloride is strictly regulated. The PCT, if you want to know, about 1,800 grams, right? About 1,800 grams of sodium chloride enter the filtrate every day, and only 10 grams of it end up in the urine. And the PCT reabsorbs about 70% of that sodium chloride. So it's a pretty incredible tube. And the first thing that you'll notice is if you were to, and you probably noticed this when you did some histology sections of the PCT, is that the epithelium is a cuboidal epithelium, and that epithelium has some of the longest microvilli you'll ever see in a cell. I mean, the surface area of the apex is phenomenal. They're so tall that it's almost like the PCT's lumen is completely covered with these microvilli. And so that allows you to add lots of proteins, these symporters, these antiporters to this. Notice that everything's driven by the sodium-potassium pump. It's going to be the driving factor of all of these mechanisms. But when you look at a PCT epithelial cell under an electron microscope, there are thousands of mitochondria concentrated in the basal compartment, right? And they're driving these, or producing the energy necessary for the sodium-potassium pumps. So we use that sodium concentration gradient to force any organics in through an organic sodium symporter. We also use sodium to drive out any protons. You're going to see this is pretty common. To drive protons out means we can prevent our blood from dropping in pH. Acidosis in your blood is incredibly dangerous. If your pH drops below 7 in your blood for any amount of time, you'll enter a coma, and if you don't fix it, you'll die, right? Because it affects the pH of all of your interstitial fluid, right, across your body. And so your kidneys are really good at using the sodium concentrations to get rid of any hydrogens we need to get rid of. We can also get rid of bicarbonate if we really need to, if your blood's really basic also, right? Using a similar sodium antiporter. But how do we get rid of protons, and how do we make bicarbonate? Well, we use carbonic anhydrase, right, to do that. So carbonic anhydrase is also very common in the kidneys and used to get rid of excess hydrogens, to get rid of excess bicarbonates. Most bicarbonate is reabsorbed back into the blood where it's already high using a sodium symporter, again, using that sodium concentration gradient. Any of the organics enter back into the blood through a basal leakage channel. So this is a glucose transporter. I think it's GLUT1. These are GLUT1 transporters, but they're amino acid transporters. They're just uniporters that use concentration gradient. Now, one of the most interesting ions to follow in the kidneys is potassium. So potassium can have major dramatic effects on your nervous system. And so it's stringently regulated in the blood. What's really cool in the kidneys is you'll find potassium leakage channels on both surfaces. And when you see something like that in the kidneys, it's basically the concentration gradient that drives it. So, what is that? What do I mean by that? I mean that if potassium's low in the blood for whatever reason, then it will be reabsorbed because it'll just enter back into the bloodstream, right? Because it's low there. If potassium's really high, any potassium you bring in will not leave through this leakage channel, it'll leave through that one, right? So when you add leakage channels to either ends, it's concentration that drives it, right? That is concentration differences between the two fluids that the epithelium is controlling movement in. Does that make sense? And so it's like built in. And this is throughout a lot of the nephron. You have potassium leakage channels on both ends, and it is whether it's high in the tubular fluid or high in the blood that drives which way it moves. Does that make sense? Urea is the same exact way. Urea will have leakage channels on both ends. So if you're producing a lot of urea, it'll end up in the tubular fluid. If you're not producing any urea, any that enters the filtrate will enter back into the blood. And so it can move pretty freely. If that makes sense. Now, I told you how we get sodium in, right? It's pretty easy. We use the sodium potassium pump. So this is transcellular movement of sodium, right? Chloride follows paracellularly, so it follows sodium. You see that? So there is a paracellular uniporter here that chlorides are attracted to the sodiums and they move back into the blood as sodium goes across. Now the nice thing about that, because I just threw out a bunch of stuff at you, is doesn't it look a lot like the gills? I mean, it's working very similarly, right? To how the gills work. And this is how we move all our organic nutrients and most of our ions back into the blood. Questions? All right, so here's our nephron, right? We have a mammal here. We have a loop of Henle. So we talked about how we filter fluid. We get it into the PCT. Now, the one thing I haven't really talked about yet, and I've waited to, is the osmolarity, right? We know that the osmolarity of the interstitial fluid in the blood is 300, isn't it? We're just using that number, right? 300 is our kind of our average. So notice, what I want you to notice here is I just told you that we reabsorb 70% of the filtrate, a bunch of water, right? 70% of the water, 70% of the solutes. We do it in equal proportions. Do you see that? We're moving just as much solute as we are water. So we're not changing the osmolarity of the filtrate. So it's not surprising that the osmolarity of the filtrate at the top of the PCT is 300, and at the bottom of the PCT is 300, right? Right? Now, there's a lot less filtrate there, but the osmolarity is the same. Does that make sense? So we've moved solute and water equally as we enter the descending limb of the loop of Henle. And we know that that's going to drop down into the medulla, right? The deepest part of our kidney tissue. It's going to make a hairpin turn and then ascend back up and become the distal convoluted tubule, right? Proximal attached directly to the glomerulus, distal not directly attached, right? Now notice what happens. 300. Now as we go down the descending limb, 400, 600, 800, 1200, 1400. So what has left the filtrate? As we go down the loop of Henle, why are these numbers going up? What is leaving? So that's solute concentration, right? 300, solute concentration is going up. So what are we losing? Water, exactly. Yeah, so the descending limb is permeable to water only. All right, and so water leaves easily here. And it leaves because the medulla is very hypertonic to the filtrate. So as we drop, what are we doing? We're concentrating our filtrate, right? Is what we're doing. We're getting rid of water, right? And concentrating our filtrate. And when you get down to the bottom, notice the filtrate is about 4 times that of blood osmolarity, right? It's a little over that, but about 4 times more concentrated than the blood osmolarity. Now notice what happens. As we come up, we go from 1400 to 1200 to 800 to 600 to 400 to 100, right? At the top of the ascending limb. So now what's leaving? The solute, right? Specifically, what's leaving is sodium chloride mostly. Okay? So sodium chloride is allowed to leave, and it's going to basically leave for a little while, and then it's going to reach equilibrium. And notice that half of your ascending limb is really skinny, right? And then the top half of your ascending limb is very fat or thick, right? And so they're called the thin loop of Henle and the thick loop of Henle. So the thin loop of the ascending limb is the first part of the ascending limb. The thick part of the loop is the top part of the ascending limb. And the epithelium thickens. That's why it widens. It looks wider. And that's because the top part here is pumping sodium chloride against its concentration gradient. Now, by pumping sodium chloride out, what we're doing is we're adding a whole bunch of it to the medulla, right? And by adding a whole bunch of it to the medulla, to the medullary space, we'll make the medullary space or the medulla very hypertonic to 300. So the job of the loop is it's a countercurrent mechanism. You have 2 fluids moving in opposite direction, and what that'll allow me to do is to concentrate the solute, first of all, by allowing water to leave, which gives me a very hypertonic amount of sodium chloride, and then it can leave and enter the loop of Henle. Can leave the loop of Henle and enter the interstitial space. The interstitial space is usually somewhere around 1,000 to 1,100 milliosmoles. And so if you think about that, if I give you a number like that, then at first you can use the loop, it's to just allow sodium chloride, the ascending loop, to allow sodium chloride just to leave by diffusion, right? Because it's a little more concentrated than the actual medulla. But as you hit 1,200, 1,000, then all of a sudden you get about midway point here of the thin loop, and you've really lost your diffusion power because now they're equal, right? They're at isotonic. So I'm going to have to thicken the loop and add a sodium pump in order to pump sodium into the medullary space to keep this exchanger giving it a sodium chloride power, if you will, to pump sodium chloride into the medullary space. So we've used this term countercurrent exchanger before, right? Where we have 2 fluids moving in opposite direction, which will allow diffusion to happen across the entire length of the loop, right? But now we actually have a new term we're going to use. It's called a countercurrent multiplier. A countercurrent multiplier. Because multiplier means you're using energy to pump sodium chloride out. So it's much more effective than just an exchanger, because the exchanger only works in the thin loop. The multiplier allows me to top off the sodium chloride concentration in the medulla. So the whole job of the loop is to remove, well, there are two major jobs of the loop. To concentrate the solute, or the filtrate, right? To concentrate the filtrate, and to add sodium chloride to the medulla. By doing that, by making the medulla very hypertonic, I can then tweak how much water will actually end up in the urine, because notice, as my ascending comes up and it passes back into the cortex, it will then empty into a collecting duct, right? That collecting duct, what does it do? It dives right back down into the medulla. So now I can use this tube to tweak how much water actually ends up in the urine. Right? That's where we'll start tomorrow.